My name is Melody Hawkins, 8th grade science teacher at Vine Middle Magnet School. This is week 2 activity packet. Today's activity is 8th grade science. The handout that accompanies this video can be found on the Knox County Schools website under the Student Resources tab. And if you need a printed copy of this activity, they will be available at the meal distribution sites each week on Mondays, 10 a.m. until 12 p.m. noon. Today we will talk about this standard. Evaluate data collected from seismographs to create a model of Earth's interior. Let's think about this as we get started. How low can we go into the Earth? Can we actually take a journey to the center of the Earth? Scientists have always been just as interested as going into the Earth as they have been with leaving Earth and going into space. For the last 50 years, geologists have tried to develop technology that will take humankind deep into the interior of the Earth. And in 1970, geologists took on this challenge of drilling into the Earth by entering through the Kola Peninsula, which is located east of Finland in the far northwest corner of Russia. The Kola Super Deep borehole was just 9 inches in diameter, but at 40,230 feet deep, which is about 12 kilometers, it reigns as the deepest man-made hole on Earth. And it took almost 20 years to reach that depth. But unfortunately, it was abandoned in 1992 due to higher than expected temperatures and pressure. The team of geologists never made it much further than less than 1% of the distance to the center of the Earth, proving that traveling to Earth's interior is a nearly impossible goal. We have learned that Earth's interior is responsible for many geologic events, such as plate movement, which can lead to continental drift, and the formation of mountains, valleys, and trenches. Studying the Earth's interior is also an important factor in understanding the processes that cause earthquakes and volcanoes. This information can keep us prepared for geologic events in the future. So how do we know so much about Earth's interior if we have never actually been there? This school year, we have learned that seismic waves from earthquakes can provide evidence about the composition of the Earth. And today, you will know you are successful when you can use evidence from seismic waves to develop a model of Earth's interior and use that model to construct conclusions about Earth's interior structure. Let's start by reviewing what we know about seismic waves. Seismic waves are vibrations produced by earthquakes. These vibrations are carried throughout Earth when an earthquake occurs. The speed of seismic waves and the paths these waves follow reveal clues about the structure of Earth, just as the path of these ocean waves reveal the island shown in this diagram. Seismic waves are measured by using a tool called a seismograph. An example of a seismograph is shown here on the right. Seismographs measure the amplitude or energy of earthquake waves as they occur over a period of time. The x-axis tells us how long the wave will last. The seismic data on the left shows the 2 types of seismic waves that have been key in giving us information about the Earth's interior. They are called P waves and S waves. During an earthquake, P waves are the first waves to be measured on a seismograph as they travel through the Earth. P waves can cause damage to buildings as they compress and expand the ground, kind of like an accordion. S waves are the second types of waves to be measured on a seismograph during an earthquake. S waves are more dangerous and can cause more destruction. But perhaps the most important quality about P and S waves is the differences in their pathways. P waves can travel through both solids and liquids, bending and refracting when they approach liquids, whereas S waves only travel through solids. This information is really important in our knowledge of Earth's interior. Using data collected from seismic waves, geologists have learned that Earth's interior is made up of several layers that vary in temperature, size, pressure, and composition, meaning the state of matter, solid or liquid. The crust that we live on is a layer of solid rock that includes dry land and ocean floor. It's kind of like the skin on an apple, and it's very thin compared to the other layers. Under the ocean, the crust is 3 to 5 miles thick, which is about 8 kilometers. But beneath continents, the crust is 25 miles or about 32 kilometers thick. The next layer down is the mantle at about 1,800 miles or 3,000 kilometers thick. And it's made of very hot, semi-solid rock. Even deeper into the earth is the core, which is mostly iron and nickel. The core consists of an outer layer and a solid inner layer. But again, how do we know this if geologists have never been more than 12 kilometers into the crust, which is not even halfway through the crust? Seismic wave data provides the proof. So how can we use P and S wave seismic data as evidence for the Earth's interior? Well, let's take a look at the seismic wave data shown here on the left. This data represents the waves of an earthquake that has occurred and was felt at 4 different locations: House A, House B, House C, and House D. If we remember that this line represents the amount of time that has passed as seismic waves travel through the earth, then we can match the seismic data to the locations that the waves actually reached. Because House A is located the closest to where the earthquake occurs, we can conclude that the second set of data belongs to House A. House B is located a little further away from the earthquake than House A, so the waves will take a little longer to appear on the seismograph. Therefore, the first set of seismic data belongs to House B. House C is located even further away from the earthquake, so the fourth set of seismic data corresponds to House C. This would mean that the third set of seismic data belongs to House D. Notice that there is a very small P wave and no S waves at this seismic location. What does this mean? Why did the S waves not appear? That's right, because S waves did not reach House D. Remember the previous chart about the differences between P and S waves. S waves do not travel through liquids because they are absorbed instead. And because the S waves do not appear at House D, we can conclude that there must be liquid areas in the Earth's interior. According to this diagram, which layer in Earth's interior is liquid? That's right. The outer core is actually liquid. And thanks to seismic waves from earthquakes, we can construct that conclusion. In the Earth model here on the right, we see that the only houses to receive both P and S waves from the earthquake are houses A, B, and C. The seismograph located at House D will only receive P waves. The S waves are absorbed by the liquid outer core. Now it's time for you to review this information by completing the activity in your Week 2 packet. If you remember our goal for today, you are going to use evidence from seismic wave data to develop a model of Earth that shows the path of P and S seismic waves, and use that model to construct conclusions about Earth's interior. You will need your Week 2 handout to complete this review activity and a pen or pencil. In this review activity, there are 4 seismographs at different locations on Earth: A, B, C, and location D. An earthquake has occurred near location A and measured by seismographs at the four different locations. In part one, you will analyze and interpret data from the four seismographs. And you will do this so that in part two, you can develop a model of Earth's interior that shows the path of P and S seismic waves. Consider these questions as you work. When analyzing the seismic data in part one, what do you notice about the type of seismic waves that consistently appear first? What can you conclude about the speed of P and S waves? How do they compare? Does every set of seismic data show both P and S waves? If not, what does this mean about the material through which these waves are traveling? And how can all of this evidence support what we know about Earth's interior structure? Once you complete this activity, you can check your work using the answer key to see if your thinking is on the right track. Once you finish your activity, see if you can use what you have reviewed about seismic data and your Earth model to explain to someone else why earthquake waves are so important. How do earthquakes give us information about a place that no human has ever been? Do you think we will ever be able to travel to the center of the Earth? Thank you again for joining me today for the 8th grade science week 2 lesson on evidence of Earth's structure. Remember, you can find these lessons and activities on the Knox County Schools website under the Student Resources tab. And you can also receive a printed copy at meal distribution sites on Mondays from 10 a.m. until noon. Stay safe and healthy, and we will see you again next week.